Hey everybody, welcome aboard. Mr. Smith here. What I'm going to do in this AP Physics slide deck, series of slide decks actually, is to work through three chunks of examples that break down all the different types of circular motion problems you're likely to see. And we're going to jump right in and begin with ones that don't involve any numbers at all, but they review the concept. So from the bad old days of amusement parks, you had a thing like this. This is Revere Beach, turn to the 1900s. This is a ride called the Wheel of Fortune, where people did exactly what it looks like they're doing. They would whirl around at increasing speed until all the riders were hucked off. It was really dangerous. You'd never have it happen today. But the big thing to remember in all circular motion examples is that what you've got going on is not a guarantee that force centripetal happens, because force centripetal is really just a mass times acceleration. It's not actually a force. And what we've got going on typically is something like inertia, like this person's tendency to travel tangent to the circle and off of the ride going on, and some kind of force needing to pull in. So the thing you want to ask yourself in all these questions is what kind of actual forces, what kind of real life pushes and pulls could be going on that could provide this turning force that we're talking about. So that's got to be the overall mindset you have as you walk through these examples. So to begin with, here's a slide that talks about 5 different kinds of forces that can really supply this centripetal force. Tension is a force supplied by a string or a wire. Force normal is a force that's supplied by a surface. Weight is the force of gravity. We break out gravitational force because when we talk about things like orbital motion that we're not into yet, orbital motion is going to be supplied by the force of gravity, even when objects are not close to each other. And then finally, as a one that you wouldn't think of necessarily, but we have an example of an airplane doing a flip. In this case, lift can provide either an upward force or a sideways force or a downward force, depending on which way the airplane's traveling. So what we're going to do in this series of slide decks is to give you some examples that are really basic, really all worked out, like this one. So I'm not going to dwell on this. I'm just going to say this slide gives you all the formulas you should have under your belt now. The biggest thing that we did was to talk about frequency and time, meaning period, as being reciprocals of each other. And this is where we always start when they give us time information. We need to get to this period so we can then go up and get velocity and so forth and work our way out to what does centripetal force need to be. Okay, so we'll take a look at that and slide right on. But one of the examples we covered in class is this one right here. And if we treat this in a really simplistic way, we can talk about simply the turning force that's required to keep this hammer from flying off tangent to the circle like that. And I'm going to pause and I'm going to fill this slide up with information, and I think none of it will be a surprise to you. Okay, so what we've done now is to take the information that they gave us. The first place we jumped on here was 36 RPM. And 36 RPM is a frequency. We came down and converted that into a period by taking 1 minute and dividing it by 36 revs, and we came up with 1 2/3 seconds for the period. Went to work, got V equals 2 pi times the radius over t, got 9.4 meters per second as the velocity of the hammer. Went forward to the next formula, centripetal acceleration equals V squared over r, and plugged that all in, got 35.5 meters per second squared, and then finally figured out the force centripetal. But this slide for me is really important because what we do is we start to make a dividing line now between force centripetal as some kind of mysterious actual force and what it really is. It's really just an m times a. It's something that we hope to get. And so really, centripetal force may or may not happen. It depends on how strong this guy is. And what you can clearly see in this example is this man is pulling inward with some great big force radially this way. That's a tension force. So it can be supplied by ropes, strings, arms, and what we've got going on in the next slide is where we're going to really bring this forward. Okay, so what we're going to do now is to contend with the real live fact that the tension force is actually the force that supplies that FC that we're hoping to get. And that tension force happens because Hamish is pulling on this rotating mass along a vector like so. And what it does is it sets us up for two things, hopefully, that feel like common sense now. The center of this mass is pulled downwards by the weight of that mass. So I'm going to draw a vector down here that's called the weight, and we can use weight equals mg to figure out the fact that it's just a minus 140 Newton force. So why does Hamish have to pull upward on an angle and not just straight in? It's because of this vector right here, because he has to generate by himself an upward force that I'm going to call equal to Ty for the y component of tension, and that's going to have to cancel out this 140 Newton force. So I know for a fact, because there is no acceleration happening on this side, the y version of Newton's second law, that the sum of all the y forces has to equal 0. Okay, so now what it leads us to is the fact that over in the x direction, though, there is an acceleration. There is centripetal acceleration. And so when we go ahead and draw a vector like this, we've got a right triangle of two vectors, Ty that cancels the weight, and Tx that supplies the centripetal force. And this down here is the actual force that this man is responsible for generating with his arms. Okay, so now I know from the last slide that this guy up here is the centripetal force. It's equal to 497 newtons, and I'm going to go ahead and just paste in the rest of the story right down here, because this is just vector math that we're going to do. We just go ahead and add the sum of the squares, square root that, and get that the tension force is equal to 517. We can go and figure out the angle theta, and I think I used theta here instead of x, but the angle theta is this interior angle right here, and then angle x is just the complement of that. Okay, so from there, let's go and take a look at the next example, which is also near and dear to physics test writers' hearts. That is the friction example. Okay, so before diving in on this example, I want to take and make one point that I hope really helps you out. In all of these examples that involve turning forces, the normal force term is one of the most confounding. It can be one of the most confusing things that there is. And so in the middle of this example, I'm going to stop for a second and just make a point about it. So to begin with, when we read a question about a car turning on a flat corner, it's setting us up for a pretty easy, straightforward example. I'm just going to paste it in down here. The first thing that you're going to want to do is take whatever information they give you. If they give you a velocity, fantastic. We just plug it in and get the acceleration of the car as it turns at constant speed. We go at F equals ma, and we find out, boom, force centripetal equals this number. So the key question is going to be, is there enough friction so that we can generate this kind of force right here? The big thing I want you to do is just go slow for a second mentally. And what I'm going to do is, let's keep that guy focused where he is. Make sure we do a good quality free body diagram right here. So if we turn our car into a little circle right there, we know that the car has weight. So we represent that as a downward arrow, 640 kilograms, weight vector equals minus 6,400 newtons. Think about the normal force now. Normal force is always provided by a surface. So in this case, the surface is this road right here, this nice flat road that's going to provide up force. And the job of the surface is just to push back however hard we push on it. And what's kind of weird is that normal forces almost always seem like they're infinitely strong. We usually want them to be. So if a chair is an example of a thing that provides normal force, you want that chair to provide support enough for any person to sit on it, not just lightweight people. So in the same way, we're going to count on the road to support whatever forces downward are acting on it. So in this case, let's just do a little color change right here, and we're going to get that there's actually a downward force here in this example that works in addition to weight. So we'll call it red, and we'll call it F down. And we talked in class about how that actually happens. So cars do that. And that force is equal to negative 4,000 newtons. And what we've just done is add to the burden of the road. So because the road's really strong, it can provide an upward force that's equal to virtually anything we put on it. And so we're going to add these two together. We know that the upward force, let's go back, I like blue. We'll go back and say that the upward force on this guy needs to equal force normal is going to equal 10,000 400 newtons. And why does that matter? Well, it makes a big difference because in this example, force centripetal is not a real force. We need, if this car is coming around turning this way, we need an inward pulling force, and the only way that's going to come from in an unbanked turn is the force of friction. We need a force of friction that's going to be strong enough, force normal, rather, let's go mu times force normal, to generate all of the force centripetal we're hoping to get right here. So we'll plug in our numbers. Force centripetal is 1.7. This is 10,400 now is my force normal provided courtesy of my road. And what does that all equal? 17,680 newtons of frictional force. And so what that means is this force actually technically doesn't exist. What happens is we ask the road for 14,564 newtons of turning force. Friction says, yup, you got it. We get the 14,564 newtons of turning force. Car sails around the turn, no worries. Okay, so we're almost done with this slide deck. We're going to take a look at one more example of turning force, one more example of normal force in action, and then we'll wrap it up for this deck. So in this example, what I'd like you to do is pause the deck, read the example for a minute before I start to explain it. Go. Okay, so in this one what we've got is a minimal information example. We've got a rotor ride, and we know that two things are happening here that should really bubble up to the surface of our minds. The first one is there's a tendency for all the riders to travel off tangent. So if you pick this rider right here, this young girl is going to tend to fly that way at constant speed, constant velocity. And it's only because of the inward force that is going to be supplied to her somehow that she is able to continually stay in this circular pathway that she's going to execute. In this case, the source of that inward force is going to be a normal force. It's going to be the force of this very solid wall that can support almost anything we ask of it, that's going to continually push inward on her depending on how fast she's going. The big thing to bear in mind is that force normal is not only capable of being super strong, it's also, again, super flexible, and it responds many times exactly the way we hope it's going to respond. So here's how we're going to start this one. We've got a free body diagram, and we're going to simulate one of the riders with a circle here. They don't give us mass for this rider, but that's no big deal. We've got weight equals mass times gravity. And if this rider right here, to pick on the girl in the peach sweatshirt, is going to not slide down the wall, if she's going to stay pinned to the wall, it's because there's some upward force right here that's acting on her. That is going to be the force of friction. So in the y direction, the sum of all the forces is going to add up to 0, and these two things equal each other. All right, now that's the sum of the forces in the y direction. In the x direction, there absolutely is some acceleration happening. It's the centripetal acceleration. So where does that come from, though? In this case, the real force that provides it, as we said, is the force normal. Okay? Now, what makes this one interesting is if we go and talk about, say, sum of all the forces in the x direction, the mathematical way of saying it is that force centripetal is just mv squared over r. That's the ma we're hoping to get. The only place that that comes from is the force normal. So in the situation where someone's traveling around a rotor ride, this is the deal. Okay, so if we put all this together now, what we're going to end up with is that at the slowest speed, what we'll call at v minimum, then let's see it. We can assemble this and say force normal, that's just what it is. Force friction, though, is going to have to just be enough to support mass times gravity. And so this is what we want to break open. Force of friction is going to equal mu times Fn, but because we know that Fn depends on our spinning speed, the mass of our rider, and the radius, we get this formula for the force of friction at F min. Okay? And what it tells us before we solve it is a little bit, should be a little insightful, that the bigger the coefficient of friction, the stronger this side of the equation becomes, the lower we would be allowed to keep our velocity, and still keep this person pinned to the wall. So if you think about it in real life, it's why amusement park riders tend to make the walls really sticky, because they're not trying to literally like knock unconscious or centrifuge or cause the riders on the ride to get dizzy or throw up. So just going in and solving this guy, we can divide out the masses, and we figure out that the v squared that we're going to require is going to equal r times g divided by mu, and so square root both sides. We get our relationship that with mu equals 1.0, and the ride radius is just, and we'll leave off the labels here for a sense of space, we've got basically square root of 20, which is 4.47 meters per second. Okay, so that's the first slide deck, the longest one. These are the most basic examples, the ones that I think should make sense, but let's talk about them in class if you like, and have a great day. Talk to you soon. Bye-bye.